And now I'd like to introduce Professor Steve Pollock, who is a professor here at the University of Colorado at Boulder. He is a 2013 Carnegie Professor of the Year, a University of Colorado President's Teaching Scholar, and although a nuclear physicist by trade, his research area is now physics education research. So he, along with his colleagues, are really rethinking how physics education works, all the way from K-12 through the graduate level. Steve is also a master wielder of blow torches, which I see he doesn't have here today. But trust me, it's a great thing when he does. And so without further ado, I'd like to pass it over to Steve Pollock.
Thanks, Deb. So welcome, everybody. Thanks for coming. I am Steve Pollock from the physics department here on campus, and we're going to take a little bit of time today to sort of maybe think about the underpinnings of COLTT. So COLTT is a conference on learning, teaching, and technology, and I find it often very useful to sort of think about what it means for students to be learning and what are the goals that we are trying to achieve so that we can better leverage the technologies that we're learning about and thinking about. I also want to begin by acknowledging the wonderful group with whom I work. This is largely folks in the physics department or connected with the physics department here at CU Boulder. We're just another research group. There's the nuclear group and the condensed matter group and the physics education research group. We're one of 7. And lots of people involved, many graduate students, many affiliates. We have collaborators in the School of Education and in the psychology department, and I couldn't do what I do without them. I also like to acknowledge my funding sources at the bottom, particularly the National Science Foundation, which pays for the research, some of which I'm going to tell you about, and also CU Boulder, for instance, through the Science Education Initiative, which has been extraordinarily helpful to us. So I got, half an hour, a little bit more to talk to you today. I want to introduce the idea of physics education research really as an example of discipline-based education research, because every discipline now has people who are thinking about what it means to learn, and I want to talk about the sort of base of research and a little bit about theoretical models. We don't have to get too deeply into that. Because I think we're here because we want to hear about practical things, and I want to show you some data, outcomes from a decade of work at CU Boulder, mostly about introductory physics, freshman physics, but also we have some lovely data where we followed students along for a couple of years. And I am not a leader of, but an active participant in K-12 teacher prep here at Colorado. It's a wonderful program. There's lots of different aspects, and I'll tell you a little bit about the way that the physics department is getting involved in helping support science majors to become future high school teachers, which is badly needed in Colorado. And at the end, I can't help myself. I'm working on upper division physics. I'm trying to understand, what's so difficult about Maxwell's equations. And that's supposed to evoke a laugh. But I have some data, and what I find the most intriguing about it is that many of the things that I have to say about freshman physics also hold at advanced upper division level. So let's just make sure everybody's clicker is working. I think that I can stop this and start it again. And so you can tell me with what field you primarily identify, and this may be a lousy list, but I took the E out of STEM, so science, technology, and math. That's a lot. I'm guessing that's a lot of us. Engineering, humanities, fine arts, and then, people don't always fit into bins. So press and hold the power button. There's a variety of clickers in the room. Thanks to the folks who got clickers here. I didn't know that was going to happen, so this is a lovely last-minute addition. And it's helpful to me, because this is an audience which I don't really know. When I teach freshman physics, I know a lot about the people in the room and where they're coming from and what they need. And so let me just take a look at what we've got here. That's not quite what I thought, so that's helpful. Here, I'll show you. Oops. I will show you this distribution. So it's a third STM and not very many engineers, and then lots of humanities, and then a third of you are other, or more than one. So you'll have to tell me afterwards what I missed. You're nodding your head. You got another? Somebody shout out another that I missed. Education. Business? Healthcare? Social work? Okay, yeah. There's so much going on. And so let me talk about physics education research, realizing that very few people in the audience are physicists, so hopefully what I have to say generalizes enough that it will be useful to you. First of all, this is kind of important. Physics education research is research by physicists. So although I have many collaborators from the School of Ed who know a great deal more about education than I do, and I suspect they think of me as a dilettante, but it's also important to have people in every discipline investigating student learning, because who better to communicate with other physicists who are teaching than a physicist? They listen to me in different ways than they will listen to people who are viewed as somehow an outsider or disconnected. And so PER, and you could replace P with whatever you like. There's history education research and engineering education research and nursing education research, right? All of these things exist. There is literature, there are communities. And I'm going to try to break this down. Of course, there's a million things. It's a big community. But I would argue that one of the underpinning studies is how do people learn? So it's a little bit of a theoretical question. Right? Is it about social interaction? Is it something that's happening in your brain? Is it you know, what's happening in this room right now? I'm just vibrating the air. So your eardrums are just wiggling at, you know, at some frequency, and somehow that frequency is supposed to make you know what I know. It's kind of remarkable if you think about that. So PER and every discipline thinks about this. We think also about how would we know that someone is learning. So now we're sort of getting into what kind of measurements, what kind of evidence could I use to justify claims about people learning? And then last, and purposefully last, is how do we help them learn? I suspect, you know, if you're like me, you're here because of number 3. I want to learn some tricks and some techniques and some ideas that will help students learn. And I guess maybe my theme here is that that's awesome and it's what we're all about, but it's underpinned by these other things, and it's really helpful to be thinking about what our goals are and what we're trying to get students to learn, and then maybe we can better address that last topic. I work in a physics department, and it's traditional in physics to have you know, labels. There are theorists. I was a theoretical nuclear physicist. There are experimentalists. And then either within physics departments or possibly connected in, say, engineering department, there are folks who apply what we're learning. You can tell that physics education research is a young physics field because there are still people who do all 3 of these things, whereas in nuclear physics, you're either a theorist or an experimentalist or you're applying the stuff, and almost nobody crosses those boundaries. So that actually makes it very exciting for me to be part of this community. Let me talk a little bit about how do we know they're learning. So in physics, people have thought a lot about what are common student difficulties. So here is an image from a test. It's the Force Concept Inventory. So for those of you who haven't had a physics course in a long time or ever, this may bring up some emotional response. Well, you're looking down. So there is a person, that's their head and their arm, and they're swinging this ball connected to a string around their head. So you're looking from above, so you can't see the gravity direction. All you're seeing is the XY plane here. And all of a sudden at point P, the rope snaps. So the question we ask of our students is, okay, which of those paths, A, B, C, D, or E, does the ball follow? So I'm not going to ask you to vote on this one. But I'm going to let you talk about it with your neighbor, because I'm going to ask you a different and more pedagogically related question. So, but think about it for a second. Just, you know, use your intuitions, your understanding of the real world, and or your understanding of academic physics. See if those 2 things are in agreement. You know, all 5 of these answers come from research. So this is 1980s, this is like early physics education research. And physicists would ask students to draw before it was a multiple choice question. Oh, this is great. Go ahead and talk. Okay, let me get everybody back together. Okay, my quip here is stop learning and listen to me. You know, it seems like people want to vote, so I turned the clicker on. Just go ahead and vote. Okay, but what I really wanted was to ask you the next. So oh, this is going quick, and oh, look at that distribution. It's good. Actually, you're doing better. Well, so yeah. Let me ask you this question. So here at the University of Colorado, I often teach the algebra-based introductory physics sequence. So it's not the engineers and the physics majors, but they're scientists. They're biology, integrated physiology, architecture, which is not science, maybe, but. So question, is this an easy or a hard question? So you can talk with your neighbor about that one. Very easy, easy, moderate, difficult, very difficult, and E, how could I know that? You know, there's a variety of meta messages here that I wanted. So only 119 people voted. Are there people who have an opinion who have not yet voted? Yes. Before I stop that? Oh, good. Yeah. So we. Okay, that didn't change the distribution very much. So the late voters are in sync with everybody else. And I'll show you this distribution. It's kind of interesting. It's pretty much all over the map. So nobody thinks it's very easy. Now, if I give this talk to a bunch of physicists, they roll their eyes and say, this is middle school physics. You know, it's Newton's first law, an object in motion remains in motion. How could anybody not get that, right? And in fact, you know, I can give you some data because we give this test to freshmen, and the answer is at the beginning of the semester at CU Boulder, it's moderately difficult. It's about 50%. So this room was about 70% correct, so good for you. At the end of the semester, they're about 80% correct. And we never ask them this question, or anything that looks like this question. We try to avoid, you know, a top-down picture of an object spinning around. We're talking about Newton's law, and we want to see if they can generalize from other situations to this one. The folks, the 20% of you who voted E, so it's a perfectly legitimate answer for this room if you haven't studied physics education research. I would say that's the correct answer. On the other hand, what I would say is if you're a physics teacher, the answer is go look it up, because there are books and articles and websites that are filled with research on student difficulties across all sorts of introductory disciplines. And so, in fact, you can find out what typical algebra-based versus calculus-based students at different institutions do on a question like this. Think how powerful that is to me as a new, you know, when I'm teaching a new class to a room that's twice as big as this one, to have some idea about what's easy and what's hard. It can really allow me to gauge timing and effort. So here is a graph which shows the learning gains on a test that has questions like that. So there's no calculations. A physicist thinks that it's high school level physics, and we give it to college students. And what you're seeing on the horizontal axis here is how much did they learn? So it's the normalized gain. It's a quantitative measure of the fraction that they didn't already know of these topics that they have learned over the course of one semester. So you give it at the beginning, same test at the end. Horizontal axis runs from 0 to, well, 1 is over here. 1 would be everybody in the class learned everything on the test that they didn't already know. And this is dismal. Okay, so this is peaking at about 25%. And this is from a paper published in 1998 by Richard Hake, published in the American Journal of Physics. So lots of physicists read that journal and learned about these results. And it was a graph. I'll show you the rest of the graph in a minute. But this graph really changed a lot about education in physics departments across the country. It was a high cultural impact paper. Most physics faculty, myself included, looked at these data and said, I don't believe it. You know, not my students. I do better than that. Because, you know, what's happening here is students are learning a quarter of what they didn't already know when they walked in the door, and, you know, on basic stuff that's supposed to be the underpinnings. So that's a little depressing, and I'll have some more optimistic things to say about that in just a sec. Why? Where is this coming from? So, you know, I'm looking at this room, and I'm thinking about whether this is structural, whether it's built into our either physical infrastructure or our philosophy of teaching and learning. So let me show you a classroom. It's a good classroom. It was very effective in its day. And, but yeah, it's 2,000 years old, so we don't teach like that anymore. Right? This room is new and modern, and the seats are more comfortable, so it's easier for you to fall asleep. But fundamentally, the philosophical, the underpinning idea about what it means to teach and learn is the same as it was 2,000 years ago, which is, I know stuff. I'm telling it to you. Now you know it. And off you go. We have a sort of a technical representation of this. So, when I talk about the conventional model of teaching and learning, the transmissionist model, which would suggest that lecture is efficient and appropriate, that's what it looks like. And there's a lot of interesting features, which I think to some extent I unconsciously, certainly bought into and still hold a little bit. The student as empty vessel. The student is passive. Learning is, knowledge is a thing. It's fluid that goes into the empty vessel, and then you're full. And off you go into the factory, right? That's the purpose. So there's a lot of wonderful and sad things about this Calvin cartoon. And I would argue that the School of Ed folks have known for 100 and many years that this just makes no sense. There's no mechanism here. And so, I would describe myself as a constructivist. I'm going to say that it's important to know what's in those empty bottles because they're not empty, and it's important that the student not be passive. And you all know all that stuff. It sort of formulates the foundation for all the reasons that you're here. You're going to these talks on teaching with technology, trying to think about ways to help make our classes not be like this. Here's the rest of Richard Hake's data. So the red was traditional lectures, and the blue is from a variety of classes using interactive engagement, which he operationally defines in his paper, which is helpful because a lot of physicists are like, wait, what exactly does that mean? There's a lot of buzzwords that get invoked, student-centered pedagogy, and there's a lot of pedagogies represented by that histogram. That's 6,000 students worth of data at a dozen universities, including Harvard, which was present both in the red data set and the blue data set. CU is not in that data set, although many peer institutions are in there. So, what do you see? Interactive engagement does 2 to 3 times as well. This is a great propaganda slide because notice that the worst of the interactive engagement classes does as well as the best of the traditional lectures. So maybe it's interesting, intriguing to learn a little bit more about what interactive engagement means. And that has by and large happened in many, but not all, physics departments and lots of other departments and disciplines. Here's Colorado data. It is a different instrument. It's the force and motion concept evaluation, but it's very similar. And, what I love about this is Richard Hake put out a physics paper in a physics journal, and it's got data. So if it's physics data, it should be reproducible. And look at that, right? It's just spectacular reproduction. And, so when people say, oh, it's education data, that's not really data. I'm like, well, yeah, I got lots of examples where education data is really data. And so lots of interesting questions you could ask. What's the deal with, this professor, and what's the deal with that professor? And, because apparently professor still matters. But interactive engagement seems to be an important part of the story. Let me actually highlight 3 of those. So at Colorado, we use clickers, we use a computer-based homework system, we have a social structure in the help room, open 9 to 5, 5 days a week. There's lots of ways in which our classroom is using interactive engagement. But there's 1 hour a week where it's called a recitation. Graduate student stands at the chalkboard, shows students how to do problems. That's how we used to do it. And then we switched to something I'll tell you more about. It's a research-based transformation. It's low tech, but it's still, I would say, a technological transformation. And these are the 3 semesters out of those 10 years when we didn't make that switch. It's not the first 3, it's not the last 3. They're scattered chronologically in there. And so that, compared to this, is really the impact of that 1 hour a week. It's quite dramatic. And then, there's still this professor who it was their first time ever teaching a large intro class. They taught it again and landed in this bin. So that's wonderful that faculty can learn. And it also suggests that, tutorials and learning assistants are no magic bullet, right? There is no magic bullet in pedagogy, and anything that you take away from this conference can best be used when you have some sort of underpinning model or understanding of why should this work and how is this working. I just got to say a word about learning assistants. So it's a program started by many people, but I will name Valerie Otero as the sort of brainchild of this program. It's been going since 2003. Dick McCrae in astronomy, Carl Wyman, Valerie, maybe a few other folks were involved in the original proposal. It is now a thriving program with many, many departments involved. Physics is just one player of many. We take an undergrad who just took the course, probably a freshman. They did well. We recruit them. They apply. We take about 1 in 4 applicants, so it's very competitive. And they come back the next semester. They take a course in the School of Ed to learn about K-12 science education, and they also run, well, they assist a graduate TA. We don't name them a TA. They're not an undergraduate teaching assistant. They're an undergraduate learning assistant. They work in small group settings. They help facilitate students. I can tell you more about that if you would like to know. I'll have some pictures of them. And about 15% of them at Colorado are now getting K-12 certified. That's remarkable. We had almost nobody in the physics department, maybe one major every 2 years was getting K-12 certified before this program. And now it's on the order of 2 or 3 a year. So it's almost an infinite improvement. So let me ask you about your thoughts about this FCI business. Suppose you could improve student performance on a measure like that. Fundamental, maybe multiple choice, underpinning. It's not really what you're teaching. It's sort of the underpinnings of what you're teaching. Should you? Is that, our job? So answer, oops, this is not running yet, sorry. There we go. So, of course, and at any cost. How about B? Sure, if the cost is low enough, and I put an asterisk, you decide what that means. How about these sorts of decisions should really be departmental level? Or D, maybe these sorts of decisions should really be individual faculty. We're talking about university teaching here. Right? Maybe faculty should decide whether it's their goal and job to be improving student performance on the FCI. Maybe they have other goals, and they should be allowed to decide. And of course, E, 4 bins, 200 people. No, it's just an asterisk, meaning it's vague, and you get to interpret it however you like. Go ahead and talk to your neighbors about this one. Since everybody's voted, let's just see if you're in agreement with the people sitting around you. And for what reasons? Okay, folks. I'm keeping the conversation short. I'm hoping that these questions may inspire some lunch conversations. Just a reminder, the FCI, the Force Concept Inventory, in physics classes, many physics faculty would say, no, that's not what I'm teaching. I'm teaching problem solving, numerical computation, calculational skill. And the FCI is sort of looking at the conceptual underpinnings. I'm going to show you this distribution too. So any administrators in the room? I like to point out that 1/3 of the people in this room think at any cost we should be doing this. I agree. No, I'm not sure if I agree. I mean, it's complicated. So the physics department has chosen D and B, I think. So there are no physics departmental decisions about whether you should be using clickers or tutorials or whether you should give the FCI. It's every individual faculty member has the right to make that decision, but we have a lot of discussions about it now. So it's not administratively decided, but I think the department has changed significantly since maybe 15 years ago, that we talk about this and make collective decisions which then anybody has the right to agree with or not. If the cost is low enough, so that's been our strategy. We teach very large lectures. The biggest now is almost 1,000 students in Physics 1. That number just keeps going up insanely fast, and we're kind of struggling to try to help keep the pedagogy productive and useful for those students at low cost to the university.
Question about your decision between A and B in the physics department.
Yeah.
So how was that decided? Like, for instance, how many TAs for recitations are there for 1,000?
Great question. So the number of TAs is a hugely important number, and that has been established through the sands of time. We've always had roughly 1 graduate TA available for every section of about 30 students. When we introduced the tutorials, I presented these data to the chair and then the dean, and we actually ended up getting support for a couple of extra TA lines so that we could just subtly change the student-teacher ratio. So the education research facilitated us and the university supported us, but it's always a battle. These things aren't automatic by any means. And as far as the LAs, the reason that physics has LAs, I came back from the University of Washington where I learned about these tutorials that I'm going to tell you about. And I went to the department chair and I said, I got this great pedagogy that we need to do here, and all I need is an extra grad TA in every room. And he laughed me out of his office. So I kind of wandered around campus, and I think it was Laura Border who pointed me to Valerie Otero, who had just gotten this grant, and they were thinking about using undergraduates to help facilitate, and I thought, ooh, good match, and it worked very well. So here is an example of a physics education research-based curricular innovation. It's a scale-up room, and many of you are probably familiar. Rooms like this are becoming increasingly popular and well-used. We have one room that sort of looks like this at CU Boulder, but I can't get access to it because it's the biologist's room. And I keep trying, but it's always full. And, it would cost, I don't know, $500,000, maybe $1 million to build rooms like this at CU Boulder. You would think, can't you just do that, Steve? And if anybody in this room can help me do that, come talk to me afterwards. So we don't have this. There's talk about it, and it happens at many other institutions, and we should. Here's what we do. So we bought some tables, and an undergraduate built those walls. And check out the technology. This is a Teaching with Technology conference. That's our technology for this 50-minute period. It's a magnifying glass, which is actually an awesome technology, and you can learn a lot from it. Oh, and a candle, right? So that's the 2 bits of technology. And there's 5 people at this table. This one with the tie is a learning assistant. And he's looking confused because, that's his role. And look, this guy is explaining it all to him, which is perfect. That's just what we want. This classroom comes from a research base. So we didn't try to reinvent this. The University of Washington has a wonderful physics education research group, one of the oldest in the country, and they've been doing research on this particular pedagogy for decades. It's probably the best researched physics introductory pedagogy that I'm aware of. It's got its own material set. It's got a novel classroom format, as you can see. There's no center of this room. That's what you do for 50 minutes. You work in small groups and then you leave. The instructional role is quite different. It's sort of a Socratic questioner rather than a teaching by telling model. And here's what our classroom looked like. 1 grad TA, many undergrads. Here's what it looks like now. So this was your comment. If you count the blue dots, it's slightly fewer. There's now an extra, and it's got a smiley face now. Because the TAs in the LAs really like this. Students, I wish I could say they all had smiley faces too, but this is hard. This is hard work. 50 minutes of thinking and not having your teacher tell you whether you're right or wrong. It's stressful, it's difficult, it's extremely successful. So, we're working hard on making it happier. Let me show you another instrument. So I showed you the force concept inventory. Here is the BEMA, the Brief Electricity and Magnetism Assessment. It's so awesome. So physics education research is one of the oldest discipline-based education research areas, which means that we've got lots of instruments like this. And in your discipline, they may or may not be as developed or even exist. And God forbid you should try to build one of those instruments. It's a lot of work. It takes many years. But so you got to get somebody else to do it. I just wanted to show you our BEMA scores over time, another example of reproducible educational data. So this is just, the score. It's slightly below 30% on a multiple choice instrument. So you might ask yourself, what does that mean? Right, 20% is monkeys. Guessing, random guessing, right? So actually, we have, I can't be like too, I can't really say that because this test is designed so it's not random guessing. Every one of those 5 answer choices is tempting, just like the one that I showed you with the ball spinning around your head. They all come from some perfectly legitimate real-world experience or idea or something you learned in another context that doesn't quite apply, but it feels like it might. So in fact, there are plenty of students who get a 0 on the first day of the semester. The little stars are the semesters when the course was taught by a physics education research faculty member. So we just get shuffled in like everybody else. Everybody in the physics department cycles through various teaching assignments. There's a couple semesters when faculty decided we don't need to give this because we already know it's going to be close to random guessing. Here's the post-test data. So that's kind of interesting. Lots of gain. So actually, on a national scale, it's a very high gain. The PER faculty members now do stand out. So, and that represents 3 different faculty. And so perhaps understanding why you're doing what you're doing and how to use those materials does help. But, you know, the flip side is it's not that big of a difference. Only a 10-point gap, maybe a 12-point gap between the worst and the best that we've done so far. So I find this, you know, both inspirational in a number of ways. And if you remember the data that I showed you for freshman mechanics, the spread was much wider than this. It was bigger than a 10-point spread. And in part, that's because we have begun to consolidate our use of research-based materials. So it's less, and if each faculty member makes up their own materials. And pretty much we're all using the same tutorials, similar homeworks, similar clicker questions. And that's making things more consistent at CU, which is another interesting story. Here's the actual histogram of the pre-scores and the post-scores, so you can see what those averages were averages of. There's a paper published which shows what the average score of a post-test would look like somewhere else. This is a traditionally taught course at North Carolina, which is in many ways a peer institution. Their students have similar SAT scores. And so their red histogram would have been peaked down here in around 40. And ours is close to 60, so you know that's good. We are in fact beating honors students who were traditionally taught. And here's another interesting piece of the story. Colorado Physics is an amazing graduate program. We got 3 Nobel Prize winners, very competitive. And our graduate TAs take this as a pretest at the beginning of the semester. And so they're doing pretty good. But actually, you know, there are students in our freshman class who are doing better than incoming top flight graduate students. Our learning assistants but of course, they had a traditional course themselves, right? This red histogram is our transform class. Our learning assistants are hired out of that red histogram pool. And as I said, it's very competitive. We can pick the best. So our learning assistants are coming in with content knowledge at a par with incoming graduate students. That's pretty awesome. And here's what's really beautiful. You know the old sage, you learn by teaching. Here's some evidence. So the graduate students certainly learn by teaching for a semester, and the undergraduate learning assistants are now better than essentially the entire distribution of freshman engineering and science majors, and some of them are going off to teach high school, right? That's really, really a wonderful thing. Had they not had this experience, there's almost no likelihood that they would have had that level of content mastery walking into the high school classroom. Let me show you another piece of data. Here, I decided, okay, we made all these changes, and we did the classic educational research blunder. I didn't give the BIMA before we made the changes. So how was Colorado doing on that graph? I didn't know. So I thought, I can give it to our juniors at the start of their junior E&M course. And so that will be sampling people who took the course 2 years ago, back when it was traditional. So that's what I did. And this went on for many semesters. And I've pooled several semesters worth of data to build up some statistics. The bottom line here is 40%. That's what you would expect traditionally taught students to be at. And our Colorado physics majors are doing a little bit better. But remember, it's a selection effect. I'm not sampling the entire population of freshmen. It's just the ones who continued on to be physics majors and are still sticking with it 2 years later. So that's where they are. It's very stable over time. But of course, by 2006, you're starting to see the wave of students who took the tutorials and the clicker questions and the homework system and all that stuff. And they're scoring 15 points better 2 years later when they're juniors. So if a colleague says to me, all this touchy-feely group stuff that you're doing, you know, maybe that's good for the average student, but I'm not convinced it's good for the physics major. Sure it is. Okay, so of course my colleagues came back to me and said, yeah, but what you're measuring here is the BIMA score, so it's still a freshman measure. So how about their performance in the upper division class? Well, that's easy to collect. Just look at their grade. So you have to be careful because every semester it's always B-centered, 3.0 on a 4.0 scale. Oh, sorry, those are my LAs, right, who do even better. There's the grade in the upper division course, traditionally taught, okay? It's always been a 3, and it's still a 3, but now the students who blew, they had a different experience 2 years ago are scoring a third of a letter grade higher when they reach their junior level in physics. So lovely data. You know, it's nice to have data like this, and many people go, okay, then you can keep doing those tutorial things. You know, how do you make this happen? We're at a big institution. There's a lot of inertia. And, you know, one way that this can happen is folks like you, who are probably like me. We go to conferences. We learn about cool stuff. We come back. You know, my students call me the human electron. And like, I want to try stuff. And what I don't want is for that to become a random walk through education space, right, where I'm bouncing. And so we'd like to be systematic. This was really an effort of Carl Wyman here through the Science Education Initiative to try to get the institution to behave in a systematic way about research-based pedagogy. So you start in the upper left-hand corner. What should students learn? In physics, we got faculty together. We had brown bag lunches, and many faculty, not all, but many came. They voluntarily spent their time. It was very powerful because with faculty goals, notice it's faculty at the center of this picture, not students. So you can argue with me about whether that's the right thing or not. But that's the Colorado model. Establish your learning goals, and then go into the classroom and look, what are students learning? So you could look at their test scores. You could use research methods, interview students, videotape students, build concept assessments, right? All that stuff is happening. And you're trying to target what are students learning based on our goals. So everybody may not agree on those things. It is only at this point that we reach the bottom, which instructional approaches improve student learning, right? Which is maybe where we tend to start. Show me something good, and let me try it in my classroom. And I'm arguing now that that's a great thing to do, and you should be iterating and building on this base, clearly articulated goals, and understanding where the students are coming from. This is a cartoon drawn by Michael Dobson, who's in the audience. He claims this is not a picture of me, but I used to have a beard, so I think it's a picture of me. Teaching students the Gaussian exponential function. And you know, how do you teach something? You think about it until it's so clear in your mind that you could just give this beautiful lecture, right? And if only I could look inside the heads of my students. And I think this is largely what COLTT conference and physics education research is about, is a variety of methods to access what's in the students' heads. And you know, all of these things are perfectly, you know, legitimate and interesting and worthwhile knowing about. The student who is asleep on the right, we're not making fun of that student. It's a reality. So I'm looking around trying to see if anybody's asleep in here. It happens in my class. You know, some of my students are working 40 hours a week and doing full-time student job. So, you know, that's useful to know about and be sensitive to as well. Okay, I'm going to start to wrap this up. I just wanted to show you one piece of data from the upper division. Here are post-test scores on a conceptual instrument aimed not at freshmen, but at juniors who have completed one semester of advanced electrodynamics. And the average score on this test, about 45%. So the physics faculty go, no, not my class. These are traditionally taught lectures, and these are the ones that have been using our research base of interactive engagement. We use clickers in the upper division. We have tutorials in the upper division. We're doing all this stuff. And this graph looks an awful lot like that Richard Hake graph of freshmen, which again is sort of helps me to believe that that's not idiosyncratic. This is what interactive engagement does. One more piece of data that I think is very compelling to people thinking about institutional change. So horizontal axis here is time. SF is spring, fall, 2004, 2005. So you're looking at a decade of upper division physics courses. So coming down here, mechanics, electromagnetism, quantum mechanics. This checkerboard is really advanced senior level electives that only get offered once a semester, once a year rather than once a semester. And I'm going to put a check mark in every box where the faculty member used interactive engagement in the form of clickers. So you might think I'm done because it's upper division, right, not lower division. And at most institutions, yeah, I'm done. That's the graph. But Colorado is a lovely place, and people are doing stuff. So PER faculty sometimes lead the charge. This was Professor Dobson, who introduced some clicker questions. And then 3 more faculty members said, oh, those look good. I like that. Let me try them. Here is a faculty member who basically did it on her own, although she did get some assistance from Mike Dobson. And then comes Carl Wyman and the Science Education Initiative and the university institutional support, right, and the conversations, and here's what happens next. So I'm not saying that will happen in your department or your institution. That would be magical. But I'm saying it can happen. and it probably does require institutional support. It's probably not, probably without institutional support, this is what the graph would continue to look like, here and there a check mark. And this is remarkable. It's not filled to the brim. Faculty at CU Physics get to make their own decisions about what they want to do. But it's pretty steady state now, and very different than it was some years ago. This is a new classroom that is hopefully going to be built in the physics building. So, it's crazy to me that this kind of environment is the environment I'm pretty much stuck in. That one is a nice compromise. To a traditional physics faculty member, they go, oh, that just looks like a regular classroom. But to me, I see all sorts of technological features in this room, whiteboards around the walls. Those desks are actually at a level where the people in the front and the people in the back can turn around and work in a group. So there's a lot of features here that people have thought about that would allow me to take advantage of some of the technological and pedagogical transformations. And takes a lot of support, a lot of money, a lot of helpful donors to build rooms like this. But, we've got some new buildings on campus that have rooms like this. They've got even more comfortable seats, and that's like what you get in the late, 2014s. Okay, let me wrap this story up. So this is a real book. It's my philosophy of teaching. I got this from Mike Dubson. Kill as few patients as possible, right? I really, that's a great motto for teaching. One of the themes here is I can't teach if I don't know the audience. This is a technology for doing that. Research is a technology for doing that. Just-in-time teaching, all sorts of things that you're hearing about this conference allow you to know the audience. I haven't said very much about student attitudes and beliefs, but it's a big part of our research effort, trying to understand student epistemology. What do they think it means to learn science? Do they think it means memorizing? If they do, they're in trouble on my exams, and I'm in trouble because I don't really know how to teach somebody who thinks that physics is about knowing stuff. So, so we do a lot of work trying to understand student attitudes and maybe even impact them. I've shown you some data, and there's plenty, and it's present in every discipline. So if you weren't aware of this, probably there's a conference proceedings in your discipline. Possibly there's a journal in your discipline. Most likely there's a website in your discipline where you can go and see what other people around the country are doing. Because I find, it's really interesting to see what a historian is doing, but I really want to know concrete, like what's the physicist doing in my class? And I find that very, very helpful. Conceptual understanding doesn't come along for free. That's what that force concept inventory and the upper division data is telling us over and over again. You have to address it explicitly, or students don't learn it when they learn to compute. And the focus here is not about the teaching, so I don't try to ever tell somebody you should teach my way, or you should do X, method X. It's more, if you think about how students are learning, it changes everything. And I do have another summary slide. So you might be surprised. Steve Pollock thinks teaching is an art, and I do. I do think teaching is an art, but I also think that teaching is a science. And I think teaching everything is a science. I think teaching history is a science, and teaching sociology, and teaching nursing, and teaching physics. They're all sciences, and it's not a dichotomy. It's not art or science. I think it's both. And maybe this is my takeaway. Teaching and research are not, and they should not be, separate missions. They're often treated that way. And I would argue that if you use your scholarly knowledge about your own discipline in your classrooms to research and understand, even if it's just micro level on your own students, your teaching, our teaching, is systematically improved. Reading what other people have done is awesome. And here I would like to end the story. Oh yeah, Professor Ratt in a seminar talking to, it's only one student seminar in history. If you could have a conversation with one person living or dead, who would it be? So the transmissionist professor might pause briefly and then answer the question, because they know what the answer is. But this is a constructivist professor who listens. So, yeah, I think an awful lot of technology in the classroom is about conversing with our students in productive ways, and I end here. Thank you.